Alright, we'll figure out something. Alright, so so today we're going to start on another functional group, carboxylic acid and nitriles.
You told us last week.
What's that?
The exam's just 18 and 19, right?
Yes.
Okay.
I think I modified it on the schedule and I said it.
Yeah, you did. Practice doesn't work.
If you want me to include 20 and 21, I can do that too.
No, it's okay. Thank you.
Put every chapter.
It's okay.
Or we can put the whole chapter till the end of the semester. And then we'll just end up early and everybody will go home.
It's still for you.
Alright, so the next functional groups we'll be considering is carboxylic acid and nitriles. Okay, so as usual, we're going to learn to name them, we're going to learn to make them, and then we're going to discuss the reaction they participate in. Okay, so this chapter 20 is basically the beginning of the remainder of the chapters that we'll be covering, because every other chapter we'll be covering is a derivative of carboxylic acid, and their reactions are going to be similar to all the reactions we've been talking about, so it's going to be just, application of the reactions and reagents that we've talked about to these functional groups, okay? So it's very, 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 very easy. Well, I shouldn't say that. But I think it's kind of easy. It's easier than what you've been doing so far. So what are carboxylic acids? Carboxylic acid are organic compound that has the carbon oxygen double bond and OH functional group connected to it. Okay, so whenever you see a compound that has that functional group, they are referred to as carboxylic acid compounds. Whereas nitriles are organic compounds that has the carbon triply bonded to a nitrogen as one of the functional groups. Those would be nitriles. Nitriles. Okay. So when you see some of your gloves, that's, I think they said nitrile gloves, right? So you can think about the functional groups that are in there, right? So how do you name the carboxylic acid functional group? The rule is similar to what we've been talking about. First, you have to find the longest straight chain that contains the COOH functional group. And you name that compound as though you were naming the corresponding alkane, but the E that ends that alkane is changed to oic acid. Alright, so for example, we have 1, 2, 3. So you're going to include the carboxylic acid carbon in the count. By the way, the carboxylic acid carbon is referred to as carboxyl carbon. Okay, but carboxyl carbon, carboxylic acid carbon, they're the same. Right, so if you look at the first example we have here, it has 3 carbons. The corresponding alkane to that is a propane. So the rule says we should change the E that ends it to oic acid. So it's going to be propanoic acid. The second example here, of course, we start with the carboxylic acid as carbon number 1. So in this case, we have a methyl group at position number 4. So it's going to be 4-methyl 5 is pentane, so it's pentanoic acid. Okay. If you have 2 carboxylic acid functional groups, so that would be dioic acid. But you'll have to start. You can start from either end. The side you start from will be determined by the substituent you have in the structure. So, for example, if you start from either end here, 1, 2, 3, this will be position number 3. 1, 2, 3, that will be position number 3. But in alphabetical order, this ethyl group comes before methyl. Okay, so we start from here. 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 carbon from octane. If that had been 1 carboxylic acid functional group on that, we would have said octanoic acid, but there are 2. So let's list the substituent we have on the chain. So we have 3 ethyl, 6 methyl, no, you don't put the numbers because they are all, it's terminal, right? Just like the aldehyde functional group. So it's octane dioic acid. Okay, so we leave the E because of the 2 consonants that will be together there. So it will be 3 ethyl, 6 methyl, octane dioic acid.
Why don't you say 1,8?
Because it's terminal, just like aldehyde, right? So it's either way, it's going to be at the end of the chain, right? So that's why you don't have to indicate the position. All right. If you have a cyclic ring, if your carboxylic acid is coming off of the carbocycle, then you will add a suffix carboxylic acid to the end of the name. So if you look at this, okay, this molecule is not chiral, all right? So therefore you can use cis trans for this, okay? So the hydroxyl group is trans to the carboxylic acid functional group. And the parent carbon chain that we have there is cyclohexane. So you're going to start numbering from the point of connection of the carboxylic acid as your carbon number 1. So 1, 2, 3, 4. Okay? So because this is trans to the carboxylic acid functional group, you're going to say trans. You indicate the position of the substituent, so 4-hydroxy it's a cyclohexane long name, right? Carboxylic acid. I'm going to write it down here so that it doesn't overlap. Okay. So this would be 1, 2, 3, 4, 5. How would you name that? Okay, but in this case you have to indicate the position. Why? Because you have double bond in the ring, right? So in relation to the double bond, you have to state where the carboxylic acid is. So it's on position number 1. Okay? Make sense? Does it make sense? For the cyclohexane, there is no double bond in the ring, so the carbon on which it's connected is carbon number 1. All right. So in this case, because the carboxylic acid is connected to carbon number 1, which happens to be the number 1 for the alkene, you're going to say 1 cyclopentene, right? Carboxylic acid. Okay.
So the 1 tells us where the double bond is, or where the...
It tells us where the carbon. So in this case, it coincides with the position of the carboxylic acid, right? Okay. So if it was on different position, then you still have to start with the carboxylic acid as your carbon number 1. Then you indicate the position of the double bond in relation to that. Okay. Make sense? All right. Cool. Oh, by the way, I'm just saying this because I don't know if. So if you look at this structure here, right? There's no chiral center, but if we move this methyl group here, there'll be a chiral center, right? So if in naming you're given stereochemistry, you have to indicate that. Okay. All right. Also, if you have a structure that has double bond and then you have carboxylic acid, of course your carboxylic acid will be carbon number 1. You have to indicate the position of the double bonds, and that has to reflect in the name. So even though we're giving you limited example here, you should be able to think outside of the box here. Okay. All right. So nitriles. How do you name nitriles? For straight chain nitriles, all you need to do is to find the longest chain, name it, and then add a suffix nitrile to the end. So for this, it's 1, 2, 3, 4, 5. Should drink water. No, you don't. Okay, so 1, 2, 3, 4, 5. What alkane is that?
Pentane.
Pentane. Going to be pentane, bless you. Nitrile. Okay, what about this? 1, 2, 3, 4, 5. A methyl group at position number 4 for methyl pentane nitrile. Okay. Well, if the functional group is coming off of a chain, you change the oic acid ending to O-nitrile, or if it's a carboxylic acid, you say carbonitrile. So what does that mean? If you have cyclohexane, like in this case, this is cyclohexane, you would have named the corresponding carboxylic acid as cyclohexane carboxylic acid, correct? So the nitrile will now be cyclohexane carbonitrile. Okay? Make sense? Alright. And then you indicate the functional groups. I mean the substrate that you have. For benzoic acid, so this is a common name that has been adopted for it, benzoic acid. You will change the oic acid at the end to O-nitrile. Okay. And then of course we have from acetic acid we have acetonitrile. That's a common name. All right. Now, in the handout I posted, this table wasn't there, so I just made a copy of it for you guys to get used to the names. For those of you that came in late, I have copies over there so you can get them. All right. So just get used to the name. the common name that has been adopted for these functional groups. Okay. Formic acid will be from your methane, right? Acetic acid is from ethanoic acid. Now, we said propanoic acid, sometimes that can be written as propionic acid. Some of you may have encountered this. The chem major that did the experiment on esterification, and you're asked to choose carboxylic acid functional groups. In some of the functional groups, the chemicals that you were using, they said propionic acid, and people were like, what is propionic acid? I said it's the same thing as propanoic acid, right? So it's the same. Propionic acid and propanoic acid is the same. Butanoic acid and butyric acid are the same, all right? So just get used to those names, okay? All right. So a copy is out there for you guys to use. Okay, so let's look at the structures and the properties. Okay, so if you look at the carboxyl carbon, so this is what is referred to as the carboxyl carbon. Okay, that carbon is sp2 hybridized. So basically, the structure of a carboxylic acid will be planar at that point, right? So because you have two faces to it. All right. So we can call that center a prochiral center too, right? You can call it a prochiral center. Okay, depending on what you perform, what reaction you perform on that center. So if you do nucleophilic acid substitution that leads to the breakage or cleavage of that carbon oxygen double bond, you'll have a tetrahedral center. So if all the four substituents that you have there will be different, that would be a chiral center. So that's why you refer to it as a prochiral center. Okay. Now, carboxylic acid has stronger hydrogen bonding interaction than the corresponding alcohol, and that is reflected in their boiling points, because you have to break those intermolecular forces holding the molecules together, so for them to boil. So that's why carboxylic acid usually have higher boiling points than the corresponding alcohol. And as the name implies, carboxylic acid are acids, so they can donate protons. So when you treat them with a base, the base can deprotonate the proton, okay, to form the carboxylate. So this is referred to as carboxylate ion or carboxylate salt. So this is the sodium sulfur, for example. So let's say you have sodium salt of acetic acid, that will be sodium what? Sodium what? Acetate. Okay? So that will be sodium acetate. Alright, so carboxylic acid are usually more acidic than the corresponding alcohol or phenol. Okay, so I can take this out, right? Okay. So they're usually more acidic than the corresponding alcohol and phenol, but they are less acidic than the mineral acids. Okay. So if you're asked to arrange compound in order of their acidity, alcohol will be less acidic than phenol, and phenol will be less acidic than carboxylic acid. Okay? Now, let's look at the factor that affects acidity of carboxylic acid. Before we talk about that, this is another independent reading that you guys have to do. I'm not going to go over this because it's something we've covered in 151, 152. This equation, right? You all know that, so we're not going to go over that. So you should read that. I made a copy for you, so read over that. It's just 2 pages, just to remind yourself of the formula and. All right, so let's look at the factors that affect acidity of carboxylic acid. What makes carboxylic acid acidic? Well, its ability to donate this proton, correct? So that oxygen-hydrogen bond is a polar covalent bond, all right? And by virtue of its proximity to this carbonyl group, if you look at formation of bonds that we've talked about in 251, that bond there is shared covalently between oxygen and hydrogen, right? So although the dipole moment is towards oxygen, which is more electronegative, correct? But the bond is holding, the electrons in the bond is holding the oxygen and hydrogen atom together. Now, because this carbonyl functional group is an electron withdrawing group, if you draw a resonance, you will see that it's having okay, so you can see that oxygen, those lone pair of electrons that you have on oxygen, is shared between stabilizing the bonds that you have between oxygen and hydrogen, and then the carbonyl. Okay, so hydrogen is not very happy in that relationship. That's why carboxylic acid can easily donate that hydrogen. So when hydrogen sees any electron-rich atom that is coming in contact with the carboxylic acid, it will leave. Okay, so that's why in the reaction that we wrote on the previous page, the hydroxyl group can rip off that hydrogen. Why? Because hydroxyl group, this is ionic bond. So those electrons you have on the oxygen are localized on the oxygen. So it can donate that electron into the partially empty orbital, s orbital of the hydrogen. Okay, it's filling that electron deficiency. So when the hydroxyl group donates the electron there, it leaves. It's happy. Okay, so we can talk about relationship in molecules too, right? You're happy in your relationship, you stay. You're not happy. Well, I'm not preaching that. I'm just saying, it's kind of similar, right? Electrons is what holds their relationship together. I don't know what holds the relationship together in humans, but there are so many factors, right? If we have to be listing those factors, we can, endless list, right? Rich versus pure, right? So you can imagine those electrons as money, if you want to, or you can think about it of, celebrity. Anyways, so that's just basic concept of the acidity of carboxylic acid. Now, how can that electron interaction between the oxygen and hydrogen be increased, be improved? Okay, or how can you deplete that electron cloud more so that it will be more acidic? All right, so that's what we want to look at now. Substituent effect. Yeah, so if you have electron withdrawing group as a substituent coming off of the chain, that electron withdrawing group will be increasing the acidity of the carboxylic acid. Why? Because it's making that oxygen-hydrogen bond even less stable. All right? And the proximity of that electron withdrawing group to the carbonyl will determine the acidity or the relative acidity of that carboxylic acid. So the closer that electron withdrawing group is to the carbonyl, the more acidic it's going to be, as you can see in this relationship, right? Acetic acid has no electron withdrawing group on. Look at the pKa. Here you have one electron withdrawing group. The pKa is reduced, so it's more acidic. You have tri-substituted, more very, very acidic. But look at the next example. Okay, so the more electron withdrawing groups you have, the more acidic it is. The closer the electron withdrawing group is to the carboxylic acid, the more acidic it is. So if you look at 1, 2, 3, 4, so that will be 4-chlorobutanoic acid, right? That's pKa. But when you go to 3-chlorobutanoic acid, there's decrease in pKa, increase in acidity. And then if you go to 2-chlorobutanoic acid, it's even more acidic. Okay? So, and the reason for that is because this electron withdrawing group withdraws electron inductively from the bonds, right? So the electrons are withdrawn from the sigma bonds. So the closer they are to where they are withdrawing the electrons from, the more acidic it's going to be. Okay? All right. This chapter is relatively very easy. Maybe I should include this in the exam, no? Nah, I'll stay with what we have. That's fine. All right. Look at benzoic acid. Relative acidity of benzoic acid. So here's a benzoic acid. If you have electron donating group, let's call it EDG, electron donating group, that electron donating group will be strengthening the electron cloud that you have between the oxygen and the hydrogen. Okay, so this is not going to be very acidic. That's why it's less acidic than your benzoic acid. But if you have electron withdrawing group, okay, that will be pulling the electron away from the system, so it will make it more acidic. Okay, so this is like a revision of chapter 16. You look at this table to see the relative activity of the different carboxylic acid. So the nitro group is the most electron withdrawing group there in the series. So you can see the pKa. And they're out deactivating, right? So you're activating, deactivating, activating the ring for electrophilic or nucleophilic substitution reaction. What do you think? So these groups are deactivating groups, right? They deactivate the rings. So what kind of reaction do they deactivate the ring for? Is it electrophilic aromatic substitution reaction or nucleophilic aromatic substitution reaction?
Nucleophilic.
It's electrophilic. They deactivate it for electrophilic aromatic substitution reaction. But they activate it for nucleophilic aromatic substitution reaction. Because for electrophilic aromatic substitution reaction, is the electrophile that is coming into the ring. So the ring has to be electron rich. And these groups are making the ring to be electron poor. So your electrophile is not going to want to come in. But if your ring is reacting with a nucleophile, which is electron rich already, it needs a center that's electron deficient. Okay? So you should go review that too. Chapter 16. Okay? Alright, so there are deactivators and activators. These are activators. Alright? But in this case, they are talking about deactivating and activating it as an acid, right? So if you have this group, if you have these groups on the ring, even though they are deactivators, they are actually making it more acidic. Okay? They are making the carboxylic acid more acidic. Let's put it there. More acidic. Okay? Because this is where you have the benzoic acid. Okay, so that's how to understand that table. So that's the middle right there for the benzoic acid, because Y is H, so that means it's benzoic acid. When you substitute that H for any of this group, it's going to be more acidic. Okay? When you substitute the H for any of the group below, it's going to be less acidic. Yeah.
So just to clarify, the deactivating groups ignore the benzene for electrophilic substitution reactions?
Electrophilic aromatic substitution reaction. They deactivate it for electrophilic aromatic substitution reaction.
Okay.
Okay? I know that those terms are very confusing, but I think I reiterated that point when we went over it. So it's been a while. I know, I understand. But review it, please. Okay. All right. That's about the properties. So how do you synthesize the carboxylic acid functional group? The reactions are something that we've talked about, so it's like a review. So if you have alkyl benzene, so basically a benzene that has benzylic hydrogen, at least one benzylic hydrogen. So this hydrogen are referred to as benzylic hydrogen. You can oxidize those alkyl benzene with potassium permanganate or dichromate to give you the corresponding carboxylic acid. Okay, but you must have a benzylic proton for it to be oxidized. So let's look at this. Here you have two benzylic protons. So this can be oxidized. Well, you can put KMNO4 or dichromate. I'm just going to use this, which is a sign for oxidation. But if you're writing your reaction, you have to write the actual reagent. Either of the two will work. So this will oxidize to benzoic acid. Okay. This also will be oxidized because it has one right there. Will be oxidized to benzoic acid. But with this, there's not going to be any reaction. Okay. Why? Because there is no benzylic proton on that carbon. Alright, so oxidation is one way to make the carboxylic acid from benzene. You can also review this again in chapter 16. Oxidative cleavage of alkenes with potassium permanganate can give you carboxylic acid. But those alkenes must have vinylic proton. So they must have hydrogen sitting directly on the carbon-carbon double bond. Okay. When you have that, this can be cleaved. You have that plus okay. So you can cleave alkene to get you carboxylic acid. Again, that's a reaction under alkenes. We talked about that. Another reaction we've talked about in making carboxylic acid is in the reaction of alcohols. Okay, so you can oxidize primary alcohols. You can oxidize primary alcohol using chromium-based oxidizing agents to the corresponding carboxylic acid. Okay. And aldehyde 2 can be further oxidized to carboxylic acid. So this is alcohol, this is aldehyde, and this is carboxylic acid.
Did you say that to get primary alcohol?
Yes. It's that's something we talked about under alcohol, right? So if I were you now, if I want to make a list of what functional group can be converted to carboxylic acid, start with benzene, substituted benzene. So alkyl benzene is one, right? Must have a vinylic proton. The other is alkene, so you can convert alkene with vinylic protons to carboxylic acid. And then you can convert alcohols to carboxylic acid, and then aldehyde to carboxylic acid. So those are 4 of the reactions we've talked about, right? What other functional group can you convert? I believe that's it. All right. Now, one reaction that we've not talked about is hydrolysis of nitriles. So if you have the nitrile group, okay, that nitrile group can be hydrolyzed in the presence of a base followed by an acid to carboxylic acid. So that's the only reaction that is new to you at this point. Okay. And I'm going to show the mechanism for that conversion under the reaction of nitriles. Okay, for now, just know that in the presence of a base or acid, you can convert base to carboxylic acid. Then we're just jumping forward here. How do you make nitriles? You can make nitriles by treating alkyl halide, secondary or primary alkyl halide, with your sodium cyanide, and you have SN2 reaction there, right? So that can replace the halogen as a leaving group to get to the nitriles, and then you can hydrolyze that to the carboxylic acid. This is nitrile, and that's your carboxylic acid functional group. So I know you know how chemistry is involved in our daily life, right? So that's one thing right there. So this is an anti-arthritis agent, simple molecule that can be made in the lab. I'm not saying you should make it, but I'm just saying it can be made in the lab. Okay. I should actually be making this in the lab, right? Then I'll use it to the game.
Thanks.
All right. So another way to make carboxylic acid, it's a reaction we've talked about, but probably you've forgotten about that, under alkyl halide. So you can actually convert alkyl halide to carboxylic acid, right? So you can make Grignard reagent with the alkyl halide, and then bubble some carbon dioxide in there, the CO2, and then with the acidic walk-up, you get your carboxylic acid. Okay, so if I were you, I'll make a reaction here that says this will be treated with the magnesium to get me the Grignard, and then I can treat that Grignard with carbon dioxide to get the carboxylic acid. So basically, any alkyl halide can be converted to carboxylic acid in this form, not just bromobenzene. Okay, you can have bromobutane, bromopropane, bromo anything, bromo any alkyl, right? treat it with magnesium, you get your Grignard, blow that in there, you get your product. Alright, so those are the few ways to make carboxylic acid. Now the reaction of carboxylic acid. See, this is awesome. See, we're almost done with the whole chapter, right? Don't worry, I'm not going to rush you through. We'll have more time to solve more problems in other chapters, so that's good. Alright, so what are the reactions carboxylic acid undergo? Well, they are acids, so they can react with base to form salt and water. Like we knew that from high school, right? Okay, to form salt and water. Organic salt in this case. And from our reaction with formation of alcohols, we know that we can reduce carboxylic acid using lithium aluminum hydride to get the corresponding primary alcohol. So we'll talk about that. Okay. So I'm going to add two reactions that were not in the book, but well, they are in the book, but in another chapter, and they are related to carboxylic acid. One of them is conversion of carboxylic acid to acid halide. Okay? So if you remember, we can treat our alcohol with tiny chloride. So let me just put it there. When you treat alcohol with tiny chloride, what do you get? You convert the OH functional group to chlorine, right? Okay, so you can do the same thing with carboxylic acid, and that will convert this OH functional group to halogen. So this will be chlorine. Okay, and these are generally referred to as acid halide. We're going to learn how to name it when we're considering the derivatives of carboxylic acid, but the general name is just acid halide. Okay, that's one there. Another one is alpha. So let me just. So the alpha protons that you have on carboxylic acid can actually be converted to halogen. For example, if you treat this with PBr3, friends of bromine, and with acidic walk-up, you can convert that to acidic walk-up or water. So you can convert this alpha proton to bromine. This is a named reaction that is called HVZ reaction. We're going to talk about it later. It's Hell-Volhad-Zelinsky reaction. Okay. So that's about it. Alright, because the preparation of nitriles involves some mechanisms, I'm going to stop here and then we'll continue there on Wednesday. Alright, so on Wednesday, please print out chapter 21 when you're coming. So we're going to continue on that, okay? Alright?
Professor?
Yeah.
Are we allowed to have a cheat sheet for this coming exam or not?
Cheat sheet.
Reference guide. Reference guide.
Oh, okay, yeah, reference card. Okay, I guess, okay.